Hey guys, hi. You are watching Simple Civil with Smriti Gupta, that is me. In this video, we'll be learning about moment distribution method and we'll be solving this question which has appeared in some previous examination. So, first point, how to understand that this problem is a sway problem. For that, we have to check upon the loading, that the loading is vertical, horizontal or both. We have to check on the symmetry of the frame. So in this one we have uneven legs, horizontal loads are there, and we have a support which is a pin support, and it is not even a symmetrical frame. So all these conditions say that this is a sway frame. So now we are coming on to the step number 1, which is fixed end moment, FEM. So what is a fixed end moment? These are the moments which are generated by the beam onto the support, which is happening to resist any deformations which are coming onto the beam. So we have your MAB, MBA, which is happening on this leg, and then we have this one that only point load is there. How to identify that we have to put a positive or negative onto a moment? So suppose, let's take an example. Let's take a beam like this. So there is a loading and this is the deflected shape. To resist this deflected shape, an additional moment will be generated onto the support which is trying to resist this deflection which is occurring. So this is your anti-clockwise. We are considering anti-clockwise as positive, and this is your clockwise. We'll be using these sign conventions onto this beam. So this is your beam and which is getting deflected like this, and end moments which is fixed, what will happen? It will try to resist the deflection which is occurring onto the beam. So what will happen? This kind of moment will generate. We are taking this as positive. So alternative, negative, positive, we'll be taking it onto the beam. So this one is positive and this one is negative. Let's understand this better. So this is our frame and we are trying to make a fixed end frame here. So I am just fixing it like this so that it behaves like a fixed frame. Now what is the quality of an intermediate joints or a fixed frame joints? So all these frames, so I have taken almost like the symmetry we are having in this frame. So these joints behave like a fixed one. So if any horizontal loading is coming onto the structure, it will affect the structure like this. So if any horizontal loading or story loading is coming, the structure will behave like this. The joints are moving in one. So this is behaving as one and it will rotate as one. You can check that. And all the supports will hold the members in such a manner that opposing moments will generate onto the support. Now talking about our FEM, so the formula what we are using here is WL by 8 for the point load. So substituting the value of W and L here, we got this as positive 30 and this one is negative 30. Kilonewton and meter, do not forget to write the units. All these things carry 2 marks at least. Be careful while putting all this, you have to write the units. Okay, so this one is positive WL square by 12 and this one negative WL square by 12. By substituting the value of W and L here, we are getting 53.33 kilonewton meter and this one is negative 53.33 kilonewton meter. If some loading is coming onto the structure, so this is our structure, these are our joints. So this joint which is intermediate joint will behave as a rigid joint. So some structure will behave something like this. We are saying that the joints will not have a relative translation, but the joint will behave as one. So if some rotation is coming, the joint will move in this manner, and no relative translation is there. The joint will behave as one. So this is the property of rigid joint or intermediate joints. So we'll be using this, and you can see this in sway frames. The structure will behave in this way. The story will move and the legs will pretend like this. So in this one it will be happening like this. Moving on to the next one, that is your step number 2 to find out the RF and DF. Now what is RF and DF? That is rotation factor and distribution factor. So these factors decide what amount or fraction of the moment has to be distributed to which part of the member in the structure. So undistributed moment occurring onto a support has to be distributed to the member joining that support to maintain the equilibrium. So DF decide what fraction of the moment has to be distributed. For that we have to make one table like this. So we have two joints. You can see here B and C are the joints and these are the members. To understand how it works, we'll take a small example. Let's take a fixed beam and a simply supported beam with one end fixed. So if some moment is occurring or coming onto the structure at rear ends, so far end will try to oppose the deflection what is occurring in the structure. So far end it will try to resist the deflection which is coming. So you can understand this. This is your beam and this is making a resistance. So the resistance will come like this. It is trying to fix the beam up. The amount of moment which is coming are 4EI by L for fixed. For hinge it is 3EI by L. So we will be using these two amounts in the table and we will be identifying our rotation factor, and using that we will be using distribution factor. So your AB is a fixed one and this leg is your hinged one. We will be using CD for this one. Now talking about the RF, BA fixed will be using 4EI by L, BC fixed 4EI by L, CB fixed 4EI by L, CD is a fix and a hinge condition. So we will be using 3EI by L. In this question, EI is constant. We are only going to substitute the value of length here and we will be finding out what is our RF. Next column is sum. So we have to just sum up our RF at one joint. So next is your DF. DF is RF divided by sum of RF. So we got this as this one. Remember, at a joint it has to be equal to 1. So at B it has to equal to 1 and at C also it has to equal to 1. Next step, what we'll be doing, we are going to make a table for moment distribution method. So like this, you have to make a table A, B, C and D. So we have find out our DF. We'll be writing that DF in the space provided here. So you have to make a table and then columns like this and you have to write down the DF here. Next step is you have to find out and write the FEM what we have calculated. So the FEM what we have calculated will be writing down. So this is positive 30, negative 30, 53 and negative 53. So I'm just going to write that in the space provided. Here we are, positive, negative. Now what we have to do, at B support, this is the total amount of unbalanced moment which is coming. So this is your 30 and this is your 53. What we are going to do here, we have to sum up. So the product we got is this one. Need not to write it on the table, but just for your clarification I'm writing it. What you have to do, the thing what we came up with, just multiply it with that df and we have to write it here. So this is known as your balancing step. What we are doing, we are balancing the undivided moment coming on to the support. So we'll be doing so the sum is coming out positive. I am writing a opposite sign. Here it is negative, so I am writing positive, positive. Then multiply it and write it. So your RF into the amount of the difference what you got and just write it. So here it is your 53.33 into 0.5. Now what is the next step? Next step is we will be distributing the moments. So what is the formula for distribution? The moments will be distributed to the near end which is fixed. If the near end is your hinge, no distribution will be there. So carryover moments will be transferred to only the ends which are fixed. So your far end has to be fixed. So these are the far ends which are fixed and I'll be just distributing the moment, half of it. So whatever moments came, half of it has to be distributed. So just whatever moment divided by 2 and write it with the sign. We have to write it with the sign. So if it is negative, we have to write it with negative sign. Next step, so this one was balancing. Next was carry over. I am writing a short form CO. Now again we have to check at B support what is the unbalanced moment. This one, and it is positive, I am writing negative, negative. This one is negative, I am writing positive, positive. Now again this one multiply by 0.5 and I will be writing it here. So we have to repeat this procedure again and again until 4-5 iterations. So unbalanced moment multiplied by df and then again we have to transfer it to the far end. Here we are, so just transferring the unbalanced moment to the far end with the sign. So the moments divided by 2 with the sign, we have to transfer it to the other end. So this one was balancing and this one was CO, carry over. Again the same procedure what we are going to do. The unbalanced moment which is coming at B, opposite sign will be writing, then multiplying it with the df and writing down the moments. Then this one multiplied by the df and writing down the moments. Again we will be transferring it to the far end. Like this, just divided by 2 and with the sign only we have to transfer. Most of the students make mistake that they change the sign. So you have to be little cautious, little careful while transferring it. With the sign you have to transfer it. So this was your balancing and this was your carryover. Again balancing we are doing. This is the unbalanced moment which is coming and we will be just multiplying it with RF. So already we have done with the 3 iterations, 1 or 2 iterations more and we'll be done with it, because see our amount of the moment is decreasing in 0.18 or something 0.4. So just make it a little more. We'll be distributing it one more time and then we are done. So now what I am doing, again distributing it. This is your carry over step. So here we are, we have just make it and this is your carryover step. Now again we'll be balancing it. So for balancing, so this is positive and negative, so we'll be writing negative here. This one is positive, this one is negative. I am writing the opposite sign here. So opposite sign and then multiplied with the df and just write it. Multiply it with the df and just write it. So after this has decreased, your moment has decreased 0.04, 0.1. So now at this step we'll be just sum up all the moments. So we have to sum up and we have to be careful that at one joint left side and right side moments has to be equal and opposite. So this is negative, this is positive, it is cancelling out each other, so your supports are at neutral. Now next step is we have to take the horizontal reaction what it is coming on to the structure because of the moments. So I am drawing a loaded image of the vertical members of the structure. The moments what we have calculated, with the sign we will be putting it. So AB and BA, and this is your vertical reaction. At this point, this is 1 is 0, I am not putting anything, and this one is 31, and this is also anti-clockwise. So I will be putting it anti-clockwise, and I will be just so this one is 31.51, so I will be putting 31.51, and okay, sorry, this is your anti-clockwise. So this is your anti-clockwise, this is your 31.5, and this is 0, need not to do anything, and this is your vertical reaction, so VT. Now I'll be taking moment at a point B so that we can calculate the reaction VA and VD. At this point I'll be taking a moment. At this point I will be taking a moment and we'll be calculating. So this one is going your clockwise, so we'll be writing it as positive. The distance what it was there in the vertical member, I have written that. This one is your clockwise, so negative. So I'm writing it negative. This is positive or negative, we have to just write it what moments came in our calculation. This one is going anti-clockwise, so I am writing it as positive here. So moment into the distance is equal to 0. So just put it in the calculator, and VA came out to be this much kilonewton meter. Do not forget to write the units. And we'll be doing for VD, just taking the moment. So this one is your clockwise, negative. Then your moment is equal to 0, so VD came out to be this much. So we have VA VD. Now we'll be calculating our horizontal sway force which has occurred because of the loading condition what we are having. For that we have to make a figure like this. So we are going to calculate this X. So this is our loading condition. We already got VAVD. What we are going to do, we have to just sum up all the horizontal forces here. So these three are going in the negative direction, this one positive. So I am just going to write it all negative is equal to 0, and here this is the value of VAVD. Just put that in the calculator and we have the value of X here, that is the sway force because of the loading. Up till now what we have done, we have calculated FEM, then we have calculated RF and DF. After that we have used that and make this moment distribution table and find out the final moments which is happening because of the loading condition. And with the help of that we calculated a X force which is happening onto the structure because of the loading. After this what we have to do, let's understand that with a small example. This is a fixed wing which has settled down by delta. So these are the moments which are generated onto the beam. This is because of the settlement, and this is opposing the deflection which is coming onto the structure. The amount of moment is 6 EI delta by L square. So let's understand it. I'm using the frame and I'm going to explain what we are going to do for the geometry condition. So this is our frame, exactly what we are analyzing. This is somewhat like this, and I have fixed it so that a little fixed end came up. Now at this point some moments are generated, so our frame will shift like this a little bit. So if we are putting a moment at this point or a horizontal force we are putting, our frame will shift like this. So just understand this. This is a frame and this is your beam. This is happening like this. So some forces or moments are generated at the far end which is opposing the deflection which is happening, which is occurring. This kind of moment will be generated which is anti-clockwise. We are taking anti-clockwise as positive. So we will be considering these moments as positive. Now let's understand by making the frame. This is our frame what we are analyzing. This is the story. The sway moment, the sway force what is coming onto the frame is happening in this way. So this member will shift here and this member will shift here. But since this is a rigid joint, so members will form in such a manner that there is a moment which is generated onto the structure, same as the beam. So these are all positive and in the anti-clockwise direction. So the amount of moment what we are having is 6 EI delta by L square. We will be using this funda or formula to understand the amount of moment because of the geometry of the structure which is coming onto the figure and giving a little bit more sway. So your MAB, MBA are having same positive 6 EI delta by L square moment which is occurring because of the geometry of the structure. DC is 0 and this one is 3 EI delta by L square because it is a hinge. So because it is a hinge, half of the moment will be transferred. So we have to write it like this. So now I am just substituting the value of L here. So this is your EI delta. Similarly, for the second one also we will be substituting the value of L here, and so this one came up to be 3 by 9 EI delta. Now in this one we have to make some assumption because EI delta value is not given. So for EI delta value, let's assume we can take it as 100, 75, 25, 50 or any amount. So in this question I have taken EI delta as 50. This is the assumption what I am doing here. This could be any amount. You can take any value what you like. So in this one I am substituting EI delta as 50. So your MAB and MBA is coming out to be positive 18.75. MCD is coming out to be 16.65 kilonewton meters. So now we have to again analyze the full frame using these FEMs. So again I am going to make that table like what we have done before using the same DFs. So here we are, same table and DFs what we are using are same what we have calculated. So half and half 0.5 we'll be putting that, and now I'll be using these moments as FEMs, and now here I'm writing it. Now we'll be proceeding the same procedure what we have done in our last table. So the moments at B joint are positive, so we'll be taking opposite sign. Just multiply it with the DF and write down. So the unbalanced moment into DF and just write down in the balancing row. So the same procedure we will be following. Transfer it to the far end which is fixed. At hinge we don't have to transfer anything. So half of the amount we will be transferring, opposite sign we are writing here, and again multiplying it with the DF. This is our balancing row. Now carry over, just multiply it with the DF and write it down. So now next is we have to transfer half of the amount to the far end, that is your fixed end. Nothing will go to the hinged end. Half of it with the sign we have to transfer it to the fixed end which is at far end. Again balancing, so this is the unbalanced moment, opposite sign we have put and just multiply it with the DF and I am writing down. Multiply it with the DF and I am writing down. So you can see the things have gone down to 0.5 something. Here again we are going to do one iteration. We are just carry over this to the fixed end. Nothing will go to the hinged end. With the sign, half of it I am transferring it. So this is your carryover. Now we'll be doing balancing again. So this is the undivided or unbalanced moment at B and C support. Opposite sign I am putting, multiplying it with the DF, and I am writing down. So you can see that the things are now decreased to the decimals, 0.131. So one more iteration we'll be doing. Just balance it and then carry over it. So now I am transferring it to the fixed end. So your A, B and C are fixed. D is your hinged. So now half of it with the same sign will be transferring it. Here also half of it with the same sign I am transferring. Now opposite sign I am putting, multiplying it with DF. So the same procedure we have to follow, and we have to do at least 4 to 5 iterations or cycle. After that we can see that it is now gone into 0.037. It is like very small amount. Now we'll be summing up all the columns what we are having. You have to make it sure that at B and C supports, the moment should come equal and opposite, that is positive, negative. It should be neutralizing the support and making it equal to 0. So see, you can see it is negative, positive, and it is neutralizing it. Now the next procedure is we will be finding out the horizontal forces or reactions what it is coming because of the geometry. Here we are. So we are just drawing the moments what we achieved, and with the sign negative or positive we are substituting here. VA is your horizontal reaction at AB vertical member. So this one is 3 and I have make it a little longer. This is your 3 meters, pardon me for that. This is your 3 meters, this is 0, and your horizontal reaction is your VD, this one. And now what we'll be doing, we'll be taking the moment at B and C point, so that we can extract the value of VA and VD. So this one is going in the clockwise direction, so negative. Now we have to just add the moments. Many students, what they do mistake is they multiply the distance also in the moment. Moment itself is a amount. We need not to again multiply the distance in the moment. Directly take the moment as it is. Put the things in the calculator and you can get the value of VA. Now your VD. VD we have like this. This is also clockwise, so negative. In this way we can get our VD. Your X bar will be simply the sum of your VA plus VD, because no horizontal loading forces are there. What we are extracting is because of the geometry. The geometry which is responsible for the sway effect. So we are doing that. So this is our X bar what we got. Just add these two and we got this one. Next is your X bar and we have this X. So what we are going to do is your loading sway force what we got from the last section, part 1, and the non-loading sway force what we achieved after the calculations. We will be putting these two values. So this is your X upon X bar. So we have this 2.04 and 9.88. So your new value for the X or the sway forces what we got after putting this in calculator is this. Now our final step. So we have to write down all the moments what we are getting at the joints. So we have these many forces. Now how to write it? So our loading moment plus our non-loading moment into the factor, because this is our imaginary force what we have taken, imaginary number, because our EI delta was not given. So we are going to multiply our non-loading moment into that factor what we have got. So I am just indicating that factor with X. So here we are. we will be just taking it. You can see from the figure, we have just taken both the moments, and non-loading, what we have assumed, we have just multiplied it with the factor here. Again, we'll be doing the same thing. Next, MBA. So the loading moment what we got plus the non-loading moment what we got, multiply by the factor x. So x is your 0.2065. We have to just put it in our calculators and we'll get the final values. So now MBC, just substitute and put it from the table, and plus your non-loading moments, and just put it like that. And we have to write the moments what we achieved into the factor, and just simply put it in the calculator with the value x and calculate the final moment. Now, how we know that whatever we are calculating is correct or not? Since we have taken one assumption, your answers might little bit got different with the answers what we have in the books. So don't get afraid. Your final answer should satisfy the criteria that at a joint left side and right side moment has to be equal and opposite. So you can see in this answers what we are getting, your BA, BC are equal and opposite. You can check that this one, BA, BC, these are just equal and opposite what we receive here. So your CB and CD, these are also equal and opposite. So like that we have these answers. Thank you for watching. Please like and subscribe.